let's start the session. And the first speaker is Professor Gang from IPMU, and the title is a state integral model for SL2 Chern-Simons theory on closed hyperbolic three matrix.
Thank you for the invitation and thank you for the introduction. So I'm Dongmin Gang. So I'm Dongmin Gang from IPMU. So this talk is based on this collaboration, and so I'm physicist studying the M theory on the various background, and recently I'm mostly interested in the M theory in this background. So M theory is defined on the 11-dimensional space-time, and we are considering. So M is a three-manifold, and we choose M as a compact three-manifold, closed three-manifold, or it can be generalized to some non-complement. And this time is the cotangent bundle, and this total space from the total Calabi-Yau, and this satisfies the Einstein equation, and this is a well-defined stable space-time in the M theory. And to prove the physics of this system, I put some basic object in this M theory, which is called the M membrane, which is a six-dimensional membrane, and I put this six-dimensional object into this subspace.
So what is 1.2?
1.2 is the Euclidean and Lorentzian.
1.2.
Yeah, 1.2. Yeah. Yeah, three-dimensional Lorentzian space-time, and yeah. And so I'm interested in the situation of this system. And so this system is defined by the three-manifold. So this is why I'm interested in the geometry of the three-manifold. So especially I'm more interested in the physics of the M brane. And in the limit when the three-manifold is very small. So this will effectively give the three-dimensional theory on the M brane, which is living on this one. So in the limit, the geometric information of a three-manifold is not important, and only the topology information of a three-manifold is important. So I began to interest in the topology of three-manifold, and this is also quantum system, and so I interest in the quantum topology of three-manifold. So this is my motivation of studying this business, and in physics there are several principles, and if we apply this principle in some concrete physical system, sometimes we get a very surprising, unexpected prediction on some physical quantity in this physical system. So if the physical system is purely mathematical, such as this system, then this non-trivial prediction on the physical quantity can be translated into the language of the mathematics, and so sometimes you can give some non-trivial conjecture on the mathematics strategies. So this is how the string theorists can play a role as a conjecture generative machine in the mathematics. So in my talk, I will give some conjectures which I obtained applying the several physical principles on this system, and I will just give the result. And this conjecture is a conjecture on some physical quantity on this system, and then I will just give the conjecture on this physical quantity, and I will explain the more rigorous definition in the second part. So first, let me give the conjecture I obtained following this system. So the physical quantity we are considering is
So after M, and then there's some strange.
Comma and the comma.
That's a comma. Okay.
So yeah, I call this as a perturbative invariant of SLK Chern-Simons theory on the three manifold. Yeah, so it is it's not well defined because it is defined on the language of Chern-Simons theory. Yeah, so but there is some prior to make this more rigorous. I will do the similar things, and I will call this as the entanglement entropy, and this is labeled by K and the three manifold and some infinite series. And I call this is entanglement entropy over three manifold. And this is because that this physical quantity will give actually some physical quantity called the entanglement over this system of the empire ring. So I will call this as entanglement entropy. This is totally new. It's not totally new quantity, and there are many the previous work, many mathematicians studied that quantities. So I will give my definition in the second section, and I will just give the conjectures. I say these are well defined. This conjecture I haven't. Just proved that. Yeah. So in the sense that I will give in this second section I will give this invariant computed by some denser description of three manifold. But the description is not unique, so we should show that each description should give the same answer. And I found some check. I did some non-trivial check, but I haven't proved full generality. So it is still conjectures up to. And I also I will it's same as the previous known invariant, which is studied by the Dimopta and the Garopalis. So when the three manifolds have some good ideal triangulation. So this is some invariant computed studied by the Dimopta and the Garopalis. And this is motivated by the Dimopta's state integral model developed by and I will just give a paper, and this is contents of the green equations, and this is a content. So I like this title because it contains the quantum. So this is the quantized Riemann surface, and this quantized Green equation. So it's very cool to me. And so what in this paper they only consider SL2 cases, K equal 2 cases, and they derived some set integral model, and which is expected to give the finite dimensional integration expression for this path integral of Chern-Simons theory, and then do the perturbation around that point, and then. But this technique can be applied to general K using some work by the Garopalis again. they generalized this ideal tetrahedron to the ideal tetrahedron ring give some hyperbolic structure and some flat connection at SL2. But in this paper, they generalized the hyperbolic the ideal tetrahedron to more specific way. Then they can prove that they can give some SLK Chern-Simons some flat connection in this construction. Using this one and applying this same technique, we can keep this invariant, and also this similar things are done by the So this to apply this technique, we need a good ideal ideal tetrahedron triangulation, and so some cases such as closed manifold case, I think that this doesn't work. Do you agree with that? In the closed case, there is the ideal tetrahedron, but it is a singular, and I hope that it will give a converging answer, so you can apply to.
It's the same formula, but you use the solution of the shape equations that they satisfy the Dehn field.
Yeah. Then do you think it gives the perturbation?
It's
really?
the same formula.
Yeah.
But you don't evaluate in the geometric representation of the cusp manifold.
Yeah.
But you evaluate when the shapes satisfy the field,
Yeah.
field equations,
Yeah.
and you get power series, and they're
Oh,
supposed
really?
to be the closed. Yeah.
Then I cannot claim this one because I found that I do the computation this way and I compute my way, and I found that it gives a different answer. Classical they give the same answer, but yeah. So I don't expect that. Then I can say this is only valuable when not the yeah. And so classical part is given by and the one comment is that this work is given some not the topology inventor symbol. It also gives some invariant on the character variety. So, but in this case, we only focus on the character which give the representation of the holonomy of the flat connection, hyperbolic flat connections. So we focus on the hyperbolic. We focus on these cases. For general K cases, we focus on the character of SLK, which is obtained by the embedding of this hyperbolic structure using the principal embedding. So this is to give the whole three-manifold invariant, not the invariant on the character variety. So and this one classical part is as you may expect. This gives the hyperbolic view, difference by hyperbolic view. And one part, so is it expected to give a torsion, relational torsion? Symmetric representation over this hyperbolic structure. And this summon appears as we decompose the SUK adjoint representation in terms of SU2. Then we have this branching ratio, then we like this. And another non-trivial thing we expect is that And some asymptotic limit of Lacing torsion also give the hyperbolic volume. So the asymptotic expansion of the large K of the next order Chern-Simons invariant also is expected to give a hyperbolic volume. So first of the invariant of a Chern-Simons theory with the true.
It's the same power, same KQ.
Yeah, K, but this is the first.
But that's n equals 2, right?
Yeah, n equals 2, it's true. So there's no.
Equals 1.
Yeah.
Okay. And you conjecture that every Sn gives the same limit, some multiple of the volume?
The other one is right here.
Greater than 2?
Bigger than 2.
So, but I found that actually this is proven if we assume that this one. So people prove that the asymptotic limit of the Lacing torsion with a higher representation is to give this behavior. So this is proved by the we got this result. We got this conjecture around this years, and at the time we didn't know this result. And then at that time we thought that this is a conjecture, but it turns out to be it is proven by this paper. So this is now proven. And I think other things is especially this one is no one has tried to prove, because that secondary loop invariant is not, there's no mathematical meaning to this one.
Excuse me, what is the portion of gate symmetry?
So
Of which?
SL2.
SL2?
Yeah.
So in the right hand side there is no K, no R.
K is a summation of origin. Yeah, summation. So if we decompose the SU-K adjoint representation, and this is in terms of SU2 subgroup, and they give this summary of this representation. So this is how this obtained.
And the limit is the void.
Yeah, so people found that the torsion of asymmetry of a three manifold at large M, large A, grows something like A times hyperbolic volume with some factor.
In D, why do you put real and imaginary part? Can't you just take the whole thing and the complexified volume or not?
So I think, but this torsion is defined up to this value.
No, I know, but so that's exactly why I'm asking. So why don't you remove real and imaginary and put equals with the complexified volume and an I in the second case? Of course, multi-row applies square root of 6, and it seems much more natural. Why are you only conjecturing for 1/2?
Sorry.
It still makes sense or not?
Sorry. What's this one?
Of the imaginary part of this.
Imaginary part of this one?
Or maybe it's
Imaginary part of this one does not have a meaning because it is defined up to.
Oh, in the limit it doesn't mean less.
Yeah, even in the limit it doesn't. It doesn't limit. So this is a some
Can I ask? So this theory with SLK is not the same one as SL2 level K, right?
Yeah, it's different.
It's different.
Yeah.
It's SLK level 2.
Yeah, it's a total different.
Okay.
Yeah.
No, but it's still, I come back. I mean, you do have the formula for S0 with k times k squared minus 1. And the volume is defined up to 2 pi I. So it means that S0 should be defined up to 2 pi I times k squared minus 1. It's much more precise.
This one?
Well, from this equality, the volume is well defined modulo 2 pi I or some multiple. So it means that actually S0 is not just, it seems to be modulo pi squared over 6, but pi squared over 6 times k squared minus 1. It's a much stronger lifting. And if you have similar things that S1 and S2 are modulo something that grows like k cubed, it seems very unnatural to kill part of the volume to me. So what I'm asking is if in part A, is it possible that part A can be strengthened to well-defined up to k squared minus 1 times pi squared over 6? Because that's your conjecture C implies that for itself. So anyway, it's not important, but it seems strange to kill half the volume. So Thurston tells us it should go together.
So maybe
It's possible that there's a lifting to a more precise conference with the imaginary of the real part. Maybe.
These are the channels, and I also another extent. So I will prove the entanglement entropy of another quantity, and we consider So here the M is some three manifold with cost boundary, and we compute some entanglement entropy of this three manifold, and this is a three manifold obtained by the Dehn surgery with the coefficient slope P, and this is true for non-exceptional of P. So non-exceptional means that the resulting three manifold is still hyperbolic, and is not the case. It is called the exceptional, and So I have to prove. I haven't given the precise definition of this entanglement entropy, but I will give some for the understanding of this event. I will give some using perscective definition. I will give this one, and we define the SLK Chern-Simons theory Conjecture function Hess integral with central level K over sigma is given by doing the Hess integral over SLK Chern-Simons theory. This is SLK connections, and we are doing the Hess integral with the Chern-Simons functional and plus sigma Chern-Simons, and the Chern-Simons functional is defined by so and I will, using this notation, I can give a definition of this. One is that so we choose the K equal 1 and the sigma is for and we expand this one, we do the asymptotic expansion and the B for 0 limit. Then this have asymptotic expansion as a summation. this is called M. And here where the hyperbolic so this is actual smooth expansion of the S integral. This is of course not well defined. And in this language, this entanglement entropy is defined by.
So we distinguish capital K and small k. So these are two different parameters.
Yeah. So this is a small k and this is a k. Yeah.
What is sigma?
Sigma is sigma is
Six.
yeah. So sigma is so
Yeah, it's a better
and
Nobody's B?
B is some formal parameter and we will do the
yes.
yeah, B is the formal parameter. And I will define the entanglement entropy by this minus rho. I hope so I have it in the place. And the minus absolute value and G K equal 1 and sigma equal 1 plus B square and 1 minus B square.
Can you write smaller?
Other black hole.
Maybe other
Yeah, we have lots of. And I will define by the E M and minus log of Z of M of SL2 and K equal 1 and the sigma equal 1 plus B square and 1 minus B square and taking this and the limit equal 1 cases. Equal 1 cases. So actually this kind of computation for when the n equal not component cases, so people develop technique to them state integral, and using state integral, I found that some mathematicians here, Kazak and Garpali studied some computation of state integral evaluation state integral model at the rational value b. So here we take the b equal 1, and I define this as entanglement entropy. So yeah.
Excuse me. So this is not the same as the volume of M.
This one?
Yes.
Yeah, this is not the same as volume of L. This is a kind of quantum volume. So this is the classical in Chern-Simons classical limit corresponds to Haber goes to zero limit, and the Haber goes to zero limit is the B goes to zero limit. And when the B goes to zero limit, and we can run state integral model, we can obtain some classical hyperbolic volume. But this is a totally opposite limit when the B equals 1 limit. So this is a purely quantum partition function. So this is difficult to evaluate.
When we evaluate state integrals at b equal 1,
Yeah.
we do get the classical volume.
Oh, really?
Yep.
Combination.
The combination of the classical volume
Oh, really?
and the one loop term.
One term only.
Yeah, only.
Can you prove that this is all in generality, or you prove it only some
For
example?
one-dimensional state integrals.
I see. In the cases, so
Figure 8, like.
So in this one, and so if we replace this is volume and this is zero, then this is just nothing but the theorem by Thurston, which said that if we do the filling space, dense filling, then always the volume should decrease. And this is a kind of a quantum version of the volume, and so this is quantum correction. So
And this correction is because the one loops do not agree.
yeah. Yes.
And this invariant was first defined when and by who?
This one?
Yes.
This one is defined into some physics. Yeah, so physics, I erased here. So people start to studying the physics theory living under this space-time, and we compact by the three manifold, and we effectively get the 3D theory. This is denoted by T, N, M. Sorry, T, G, K, M. This is labeled by number of fiber and the three manifold. And the people found that the relation that some physical quantity here is related by some Chern-Simons function here. And some physical quantity, some called some entanglement entropy, is well known in mathematics, is in physics, already known before, even before this one. And found that they found that relation that the entanglement entropy can be mapped to the SL2 Chern-Simons theory with the p equal 1 limit. Yeah, so.
And when it was done? Which year?
This one, the entanglement entropy. So the story is complicated. People found that first found the 3D correspondence. People found that some action function of this T and M 3D theory on curved space-time is related by the Chern-Simons particle function. Okay. SLK with K equal 1 and the sigma equal. Yes, this is found by the Masaito and the Terashima and the other groups is around the. And then the people found that when the D equal 1 case is this SB, maybe SB is some three-dimensional geometry which is covered by this geometry called squash here. And so we consider this 3D theory on this curved background and compute the partial function.
C squared, right?
Yeah. And then around the several around I don't remember correctly. People found that this when the p equal 1 cases, and this value is a very important quantity which has a good property in the some so-called algae learning, and this is also people found it is identify the entanglement entropy. So if you compute this partial function, for me the most important value is when the p equal 1 cases.
So what you call EE of M is what Don Zagier was calling yesterday E to the capital C.
Really?
Yes. He had an identity among divergent power series that are converging inside x equal 1 in a disk. And that's E to the capital C is your
So there
EM.
So there is some.
That was the limit B equals 1.
Oh, really?
Yeah.
Really? Oh, it's very interesting. I didn't know that. Yeah.
Which is still Q equal 1, right?
Yes, Q equal 1.
Yeah, and we are computing quantum algorithm with a Q parameter and the Q tilde parameter.
Yeah.
And we are taking both of them out.
Yes.
Yes.
So is the limit that we know the answer?
Yeah.
Oh. Oh, I see.
And I have to ask, have you thought of the limit when Q tends to -1 or some root of unity?
This is the little k.
Yeah.
Is that the
little k, not the big k. There is a little k.
Not necessarily. See, you can play with B.
See? So,
Even little k is not enough to get all natural numbers. It's just one.
K stays
K
the
rational.
Little k is the k root of unity.
Not only.
Yeah, but I don't have a k over here. You have a rational number. It's not just one.
So that's a rational body
Well,
called
one is not there.
where quantum daro plus classical daro.
But if you
That's the cycle of rational numbers.
my God.
Yeah, so
Only if it's the that's right.
Like C equal 1.
So K is the
So I like this formula because I want how this conjecture is true because that if then is true, then we can claim that we quantize the theorem. So we quantize the Riemann surface and quantize the gluification. Now we quantize the theorem. So I hope so it will work. And
But this is the partition function of S we do Chern-Simons.
yeah, so yeah. So in general, we can consider this SLK, but so I think that this case is very complicated.
No, I mean the argument of log. Is it the SU2 Chern-Simons partition function of S3?
Yeah, exactly. So we derived this formula, using the return formula of the S2 Chern-Simons theory with level P.
Where P is K plus 2.
But we are, exactly. But in supersymmetric cases, this shifting doesn't appear, and this is correct. So I give some conjecture, and I should give some less rigorous definition, not using the percentile. So one way to do is that I just followed what Dimopte and Garapari did in this paper, and we just developed the state integral model, which is believed to give this partition function of this SL2 Chern-Simons theory. So we are considering three manifold, which is given by some obtained by the Dehn splitting. And the M is some closed three manifold, and we are considering not complement or link complement, and has a link has component this number of component, and we are doing some component of this boundary. We include the solid cross, and we form another manifold M. Then I will write down the state integral model. And so I use this data, and so state integral model over M. I first write down SL2 cases. This is similar. And we depend on the parameter B. And I And I use the state integral model for non-complement. So this depends on the. So we originally start from this number of a torus boundary, and we glue the solid torus this number, and so the boundary number of bounded torus is impinged by this minus this. So this is the x minus plus 1. So this is S is a number of
Is alpha?
so I sorry.
That's example.
Yes.
Is
Why S can equal number of components of that?
Sorry, it can be. And we obtain the closed manifold, and also we can do this one, and this is nothing but the original state integral model. So this interpretation, this one. So with the developed state integral model, I think that this can be applied to any not complement using the ideal tetrahedron. In that case, the ideal tetrahedron is good enough to give the correct answer. Then this for SL2 cases, this developed state integral model gives the integral expression. The final answer depends on these values. The exactly same as the number of components of the not complement. And then we are gluing the solid torus. We gluing the S solid torus. Then this is a quantum version of it. So we are doing integration of that number of the variables, and with some proper measure. So this is my proposal, and so I need to explain a little about the smooth test. And so this is based on the ideal triangulation of K tetrahedrons, and so to give this expression, we first find the Neumann-Jacobi datum. So which describe the systematic, which give a systematic way of describing these gluing equations. So gluing equation can be summarized by this one. So U. should explain the notation. Here is the logarithm value of the tetrahedron. So this is the Z is the Z1 to the Zk number of the tetrahedrons, and the Z double prime is the we label the Z1 prime and the Z1 double prime, and we give the constraint Z1 to Z1 prime Z1 double prime for I5. So then using this relation, we can integrate out this Z prime, and so Boolean equations can be written as Z and Z2 prime variables. And this U is we have L component boundary, L this number of boundaries. So this is a kind of a meridian variable, and this is the longitudinal variable. So we go. And the C is internal edges, and there are, so in general, the K internal edges, but not all of them are independent, only the K minus L are independent. So this is the K minus L internal edges. So this size is a K by K matrix. This is K by K matrix, and this is L times K matrix, or this is the S times K matrix. And this is the column with the size K, and this is column size S. And this is known as the middle and And from this data, it is known that in this Boolean equation there is some symplectic structure, and this matrix can be completed by the SP2QZ matrix. And if there is some completion, this is not unique, but this is belong to SP. And the up triangular same matrix, and this is the first L component the same, and the others are some matrix which is obtained to satisfy this condition, symplectic conditions. And so in this setup, we call this is a matrix A, B, and C, and D, and this vector U and UP, which is defined by UP hat and 0, also 0. And this we will call the Neumann target data. And there's a lot of redundancy on this from this ideal tetrahedron. There's no unique way to choose this one. There are lots of redundancy in this expression. So first we can choose a lot of we just call this Z prime and this is Z prime, and this is called the choice of a chord structure in the tetrahedron. And also we have a choice of the which internal edge we will choose. So among the K, there is a K internal edges. Among them, we will choose this number, and the choice is not unique. And it's also there in the compilation, there is no unique choice of this matrix. So this is a lot of redundancy. So using this Neumann target data, we can expertly write down the state integral model, which is determined by Chern-Simons and Nishi-Waseda. So we are calling the K tetrahedron. So this is been by integration of the K tetrahedron, K integral variables. 프로젝트 한번 같이 하려고 그랬죠. So I just like this expression because we can give the expressions. But as I mentioned, this I should define the what is f and f is defined. Is determined by the justifications, and the haba is here, and the z is so in this way we can express like on the state integral model, and in the as I mentioned, there is ambiguous some redundancy choice of the A, B, C, D, and this data. But these people developed and Rapan's carefully check that under this redundancy, this does not change much, and the change is exactly only this kind of only this change. I mean that. So this is only change. This is defined up to exponential. So they carefully check that so the ambiguity of this expression is only given by this number, only this factor, and if we change another representation, this is changed by only this factor. So up to this factor, this state integral model is well defined. They carefully check that these kinds of things.
But is it last term is real ambiguity? Imaginary. First that last one are real, right?
Yeah, so they should have a, yeah. So all the phase vector, if we put the b equal 1,
Okay, but
b equal
then the second term, second and third term, if third term is proportional to 6.
Yes.
Ah, okay.
Yeah.
And what if B is not invertible?
Sorry?
If matrix B is not invertible.
Ah, yeah, that's a good comment. And these people also prove that using this redundancy, we can always choose the B to be invertible. There is some choice of this structure which guarantee that this matrix B is always invertible.
For any triangulation.
Yeah, any triangulation, just choosing this quadrant structure, we can make it B is invertible. There's always one choice, always at least one choice. Yeah. So we can choose we will choose this, and we can always choose this B matrix maybe invertible by choosing this choice.
But I think if you eventually want to prove the invariance, that it's independent of the triangulation,
yeah, so
you should take all symplectic matrices, because when you move, you cannot preserve the condition that B is invertible, maybe. I mean, it should be a group theoretical problem. So I've said the same to Tudor many times. It would be wonderful to give a formula that does not, in a symplectic matrix, B and C together, or B and D together, are always invertible. They're co-prime because it's symplectic.
Yeah.
So you should have a formula using B and D, and this is kind of pretending that you have a case where D is 0, the matrix D is 0, then B is invertible. But you should use, there should be a formula that uses the full symplectic matrix, A, B, C, and D. It's just a comment. It's very bad to have a formula using B inverse.
B inverse, yeah.
You should use the whole matrix, which is invertible. It's got element 1. And somehow this is kind of like reducing to a special case in a sense. So even if you can always reduce, it's better to have the formula that always works, I think.
You did it. Yeah.
So for the future.
Yeah. Future first. Yeah.
Yeah, I think, for example, if it's a SL2 case, for example, and if 0 is 1, 0, 0, 1, 1, can use, for example, 1, 0, K1. In that case, the partition function is multiplied by just Gaussian function without no integral.
So this matrix has nothing to do with that K. I mean, this is just the size of this matrix is the number of tetrahedra.
Oh yeah, that's right. So that's a SP2 case, for example. So so this is SP2 times a number, for example, Mongello matrices. But they are similar generators.
Yeah, of course, the group has generators where B is invertible.
Yeah.
But I'm saying that it would be very good to have a formula, not just for generators. A group should not be given by generators relations.
Yeah.
It should be given by all the elements. So it would be very good to have a formula that works for any symplectic. It's just a comment for wish in the future. Criticism. It's hard to do. So I'm sure there is a formula that always works. Also for yours and also for yours. It has to.
Yeah, I forgot to mention that they also check that this is invariant to the 2-3 moving up to this value. So this is totally the invariant of 3D topological invariant of 3 manifold. So I gave this statistical model, which is based on the Dimorphic statistical model and the terms. And in here, there's no ambiguity. Only ambiguity comes from here. So we expect that this full expression still have this ambiguity. And but the one not trivial thing is that some 3 manifolds have some different realization, such as that if you are considering the tight-headed link. And we do there's a two component, and we first do the one component by the and to the tensor with this value, then it is known to be the same as some 3 manifold called M003, which has the same hyperbolic volume as a figure in that, but a slightly different topology. And so this high-tensor link can be obtained by gluing the tetrahedron. So applying this formula, so we are gluing the tetrahedron and the additional 1 solitors. This formula will give the fiber integration. But another way to represent the 3 manifold M003 is using the ideal triangulation with the 2 tetrahedron. And it will give the expression. In this case, we don't need to use by expression, and we can just use this state integral model, and this is 2 integration. And both expressions are totally different, but at least I checked that if the state integral model and do the perturbation, and both of them give the same perturbative expansion. I checked that this example and the many example, but I don't know how to prove it in general way. So I cannot prove that this is actually well-defined topological invariant, but I did some conscious check, and I think this is correct. Give the correct expressions. So, and by this invariant Sn and this one, this is the Sn M of this one is defined by doing the similar things what the Paris and Timothy did. We did the perturbation, and we can obtain this one. And actually, we cannot prove that this is invariant, but so we will try this one. And this entanglement entropy I did is that we evaluated this integration with the B equal 1 cycle with choosing a proper contour. And we haven't proved yet, but it seems that when this resulting 3D manifold is real, the hyperbolic case, it seems that we can always find some converging contour which satisfy the good conditions, certain conditions. So I think that we can prove that for hyperbolic cases, there is a unique choice of contour which has some good property, and then we can make it more rigorously, and we can define that this as a F, and the evaluation of the B with some contour. Let me stop here.
Questions?
But all these contractions are invertible. So can you do some, I mean, as an integral transformation, can it be inverted by treating Q alphas as mu variables, replacing X alphas?
This integration?
So can this product of signs be considered as an integral kernel
Integral.
of an operator acting on X alpha variables, giving new Q alpha variables, forgetting that Q alpha were integers? So in this slide, this looks just equivalence transformation of the most partition function to new variables.
Sorry, I found there's a critical mistake here. Essentially, this so still is a secure. What was your?
So my question, so can you think of this as an integral transformation from variables X to variables Q?
No, I see. So
And then, so you can restore the most partition function from your new partition function by inverse transform in Q variables.
inverse transform in Q variables.
Could it be true by treating Q's just like complex variables?
You do the analytic continuation with the Q variables and do the Fourier transform again. Then you will back to the.
You get back to.
Interesting. But to do that, we should know that this my state integral for every Q. To perform a Fourier transformation, we should know this is give my M hat and L and the P alpha and the Q alpha, and we should know
but this formula somehow is suggestive that it is defined analytically to complex.
It's analytically complex.
Do you have any guess on the inverse?
No, I don't. But that was my question.
So this variable it's difficult to imagine that to make this as a continuous variable and integration. So.
But if you have your integrand and you think of an integral kernel, then maybe you can.
Okay, let's start to speak again.